Good evening, students. Very good evening to all of you. I'm Umesh Thameja. I'll be discussing today about, we'll continuing with the chapter of solutions for your JEE preparation. So I'll be discussing some about all the basic fundamentals first, and then we'll be proceeding to the some multiple choice questions also. Can all of you can hear me and see my screen? Yeah. So I'm now starting today's class with the topic of vapor pressure, right? So understand here how I can discuss about this vapor pressure. Here I have a beaker and it is filled with one liquid, one pure liquid A. I say a pure liquid. When I say pure liquid A, means it is not a solution at all and it is covered. And here I have, can you identify this instrument that I'm making right now? Yeah, can you identify this instrument that I am feeding a red color? Yeah, very good, very good. Manometer. What is the function of the manometer? What is the function of manometer? To measure the pressure. Fine, absolutely fine. Good. So these are the molecules of the upper layer, and at a particular temperature T, it may be possible that these gas particles are escaping and converting into vapors. So vapors are formed. And once the first layer has been completely evaporated, the second layer is ready for evaporation. Right? It may also get evaporated. Then third layer, then fourth layer. So what will happen with the passage of time, the level of water will decrease. Are you getting me? So this level has gone down and vapors are formed. Vapors are formed, right? These vapors are formed. Now, after some time, there is no change in the level of the liquid. We observe this thing that after some time, the level of water this pure liquid does not change. Can we say that evaporation has stopped? Can we say the evaporation has stopped? Yes. I want to answer. There are 15 students in my class. Okay, some says yes, some says no. Okay, I want. Okay, fine. What is happening actually? The speed with which the evaporation takes place, at the same speed that condensation takes place. These particles they collide the wall, they collide the lid, they collide the surface. These collisions are elastic or non-elastic. These intermolecular collision are elastic or non-elastic. I have got 3 responses which say elastic. Fourth response has come, they say elastic. Do you know what is the meaning of elastic collision? What is elastic collision? Yes. Yes, they don't lose energy. Absolutely, I mean, they don't lose energy. There's a conservation of momentum also. And if it is so, their energy should not decrease. But actually what is happening here is these particles, when they collide, they lose their energy, they slow down and ultimately stick to each other, and then they're converting back to the liquid. So these collisions are perfectly inelastic. Are you getting me? So the collisions here are perfectly inelastic, not elastic. Are you clear? Everyone? Right. So due to this collision, the inelastic collision, it is liquefying again, getting condensed. I can see here the rate of evaporation is equal to rate of condensation, right? I can say it's a state of equilibrium. So these vapors are exerting some pressure on the surface. The same is applied over here. The level goes down, or the mercury here goes here up, and this is the x mm of mercury, right? So this pressure is called as a vapor pressure. So what is vapor pressure? Vapor pressure is what? The pressure exerted by vapors on surface of liquid, on surface of liquid at the stage of equilibrium, at the stage of equilibrium at a particular temperature. Are you getting me? This is the pure liquid A only. Suppose I add one liquid. To this liquid, I'm adding a non-volatile solute to it. Can you tell me what is the meaning of the word non-volatile here? Can you tell me what is the meaning of non-volatile solute? Yes, friends. Not easily evaporate. Don't evaporate. Yes, those which do not vaporize. Chitransh, absolutely correct. That do not get converted into vapors. Can you give an example of a non-volatile solute? Can you give an example of a non-volatile solute in a volatile solvent? Oil does not evaporate. Okay. Yes, Lalit, you are right now. Like salt, sugar, if it dissolve in water, then water is evaporated easily, but the sugar or salt do not evaporate. So in the upper layer, some molecules are the solute and some molecules are of the solvent. And here I have the instrument that is known as again manometer, right? So what will happen here? These non-volatile particles will not evaporate, but only the volatile particle will evaporate, right? So whatever the pressure I will get over here will be called the PS value. Can you tell me what will be the value comparison, pressure value comparison, or the pure component A and the solution, which is smaller value, the pressure solution or the pressure the pure liquid, which is smaller in value, smaller in magnitude? Vapor pressure solution is less, or vapor pressure solvent pure water is less? Yeah, it is less. Can you tell me a reason here? There are two reasons due to which the vapor pressure for solution is less than that of the pure solvent. Number one reason is number of volatile particles in the upper layer. Volatile particles in upper layer are less, right? So less vapors are formed, and we know this equation PV is equal to nRT. So temperature is constant, volume is constant, R is constant, so pressure is directly proportional to number of moles, right? So less vapors are formed, less pressure will be created here. Number one reason is this. And number two, you are done in your +1 level. Vapor pressure is inversely proportional to density, square root of density of solution. Can you tell me which is more dense? The pure solvent is more dense, more viscous, or the pure or the solution is more viscous? Solution is more viscous. So as the density increases, the vapor pressure will decrease. Reasons are not clear. Okay. Reason is, if I say I have just a pure water over here, all the particles have evaporated here. But here, some particles are of the solute particle, which are non-volatile. These are the non-volatile solute. Non-volatile means their vapors are not being formed. So only the water is evaporating, but not the salt. So number of vapors will be less or more as compared to pure solvent. Yes, Venkata? Number of vapors are less, yes. If the number of vapors are less, the pressure will also be less. Number one reason. And number two is the density of solution. More the density of solution, less is the vapor pressure. And you know that this solution containing non-volatile solute will be more dense. Right? Now, I hope it's very clear. Fine. Now, we'll discuss about the factors which affect the vapor pressure. Number one factor that affect the vapor pressure is intermolecular interaction. Intermolecular interaction. Stronger the intermolecular interaction, less vapors are formed and less is the vapor pressure, right? Suppose I say I have a water and I have an acetone. Can you tell me out of the acetone and water, which is having stronger intermolecular force of attraction? Very good. Charan Singh, can you tell me which forces are operating in water? Very good, Venkata. Hydrogen bonding. So between the two water molecules, there is a intermolecular hydrogen bonding. And what about this acetone? Between two molecules of acetone, what type of interaction is there? Between two, yes, very good. They have a weak van der Waals force of attraction, right? The weak van der Waals force of attraction. Which is stronger force? Sorry, hydrogen bonding or van der Waals? Which is stronger force? Hydrogen bonding. Perfect. So whose vapors will be formed in more in quantity at a particular temperature? Acetone or water? Acetone, right? So whose vapor pressure will be more at a particular temperature? Acetone. Perfect. I hope it's very clear now, right? Now, it means if I draw a graph of the vapor pressure, then the vapor pressure of water at this temperature T will be less as compared to the acetone here. Are you getting me, everyone? So second factor operate here is the temperature. Can you tell me what will happen with the increase in temperature? What will happen to the vapor pressure? Will it increase, decrease, remain same? Yes, vapor pressure increases perfectly. So vapor pressure increases with increase in temperature. So second factor that is there is the temperature. More the temperature, more is the vapor pressure. I hope everyone is clear, right? So basically, vapor pressure is directly proportional to the escaping tendency, or we can say the volatility of the liquid. The one which is more volatile will be more creating more vapor pressure, right? And vapor pressure is directly proportional to the temperature also. Now, very interesting fact come over here. If you draw a graph here of the kinetic energy in the molecules, at temperature T, this is the graph. But at any temperature T2, such that T2 is greater than T1, the kinetic energy of all the molecules increases. At very low temperature, no, very less fraction of molecules have very low kinetic energy, right? And very less fraction of molecules have very, very high kinetic energy also. Are you getting me? Suppose in a container, very certain number of molecules, very less fraction of molecules have very less energy. And also the number of molecules which are having very high kinetic energy, they are also in less in number. Is this clear? Is this point clear that what I'm telling now? Everyone? Okay, I repeat. This is a very important aspect here. Suppose I say this is a container here, or the room in which you are sitting right now. The room in which you are sitting right now, there are certain number of air particles in your room. Is air is in your room, or yes or no? Yes. Okay. So are all the molecules moving with the same velocity? Are all the gas particles moving with the same velocity? Yes or no? No. So which particles are moving with the more velocity, right? Some are with the very high, some with the very slow. Those number of particles which are just near the fan. These days there is a summer season, right? So there is a fan or air conditioner in your room, whatever. So those molecules which are just near the fan, they are moving with very high velocity. And the number of particles, number of gas molecules which are below or under your table or in the corner of the room, or maybe somewhere behind some sceneries in your room, the particles are moving with very less velocity. Am I right? Are you getting me? Yes. So those number of molecules which have very less kinetic energy, they are also very less in number. And the number of particles which are very high velocity are also very less in number. Those are just below the fan. But most of the space, most of the particles are moving with some intermediate velocity. And they have intermediate kinetic energy. Are you getting me? Now, if I rise temperature, all the particles will start moving with a comparatively higher temperature, higher velocity. So the average will increase, and that's how this graph comes over here. The T2 is greater than T1. This is very clear now. Now, liquid molecule also show random motion similar to gases. So same thing we can write here. Right? Same graph we can draw for the liquid also. And now suppose this is the minimum energy, minimum kinetic energy for escaping the liquid into its vapor state. Now at a temperature T1, this much is the fractional molecule which can evaporate. But at a higher temperature, the number of the molecules increases which can escape at a higher temperature. And that is why more number of particles are evaporating at a high temperature and more is the vapor pressure. I hope it's clear now. Everybody's clear? Good. It's very easy. Now, just go through this graph. This is the minimum kinetic energy for escaping into vapors. And in this yellow range, red yellow shade, less number of particles are there to evaporate. But at a high temperature T, the area under graph becomes double or triple or somewhere. Then more and more number of particles are evaporating and more is the vapor pressure. Now I'll be discussing about what is the physical or what is the quantity of the vapor pressure that will increase here. So, you know the equilibrium constant K1, it's a K2. So at any temperature T, K1 is the equilibrium constant, and at temperature T2, K2 is the equilibrium constant. You know, more the K value, more is the extent in the forward direction. You had done in the chapter of equilibrium. More the K value, more the equilibrium constant value, more is the vapor pressure. So with a high temperature, the K2 is higher than the, K2 is higher than the K1 at high temperature. It means the K value increases with the increase in temperature. And this equation is known as a Clausius-Clapeyron equation. That will tell you how much percentage the K will increase, how much percentage the vapor pressure will increase. Now, we'll discuss about another topic that is known as a ideal and non-ideal solution. Ideal and non-ideal solution that I will discuss. But before that, there is another topic that is to be discussed is the Raoult's law. I will discuss about the Raoult's law now, right? Fine. Raoult's law. For solution containing non-volatile solute. Raoult's law for solution containing non-volatile solute. Now, suppose I have a binary solution made up of two components. A is volatile solvent and B is non-volatile solute. Its weight is WA, its weight is WB. Its molecular mass is MA, its molecular mass is MB. Its number of moles are Na, its number of moles are Nb. You know, number of moles is equal to weight upon molecular mass. Now, vapor pressure in pure form. I'm saying vapor pressure in pure form is PA naught and this is the PV naught. Can I say PV naught is equal to 0? Can I say PV naught is equal to 0? Yes, students. Yes. Why I can say PV naught is equal to 0? Why can I say PV naught is equal to 0? Yes, non-volatile. Very good. So if it is a non-volatile, its vapors will not be formed and the pressure due to that component B will be 0. But if I make a solution now, and now I'm determining the vapor pressure of in solution here of A and B both, I'm representing that is PA and the PB. And again, I can say PB is equal to 0. Again, I can say PB is equal to 0, right? And now the vapor pressure solution is equal to pressure due to component A and pressure due to component B. And it is equal to pressure due to component A plus 0 because the PV is equal to 0. So PS is equal to PA only. And now I apply here the Raoult's law that states that the vapor pressure of the volatile component in the solution is equal to the product of its mole fraction and the pressure in the pure form. This is the mathematical definition of the Raoult's law. The vapor pressure of the volatile component, you can see the volatile component is of A only, is equal to the product of two things. Number one, its mole fraction. Number two is its vapor pressure. The product of the two is called as a vapor pressure of the solvent of the A component. Any doubt here till now? So can I say the PS is equal to mole fraction of the A and PA naught? So I can say PS upon PA naught is equal to mole fraction of A. So I'm going to the next page now. So I can say PS upon PA naught is equal to mole fraction of A. If I subtract these values, both sides from 1, mathematically it is not going to affect anything mathematically, but it is not giving me another property that I'll not discuss here. Can I say 1 minus XA, mole fraction of A, is equal to mole fraction of B? Why can I say 1 minus mole fraction is equal to XB, mole fraction of B? Yes, because the sum of the mole fraction of A and B is equal to 1. Are you getting me, everyone? Yes, Venkata, you are right here. Now, what is this value? Very important here. PA naught minus PS. What does it indicate here? What does it indicate here? What is PA naught minus PS? Can you tell me what is PA naught here? Can you tell me what is PA naught here? Vapor pressure of the pure solvent, right? Very good. And what is PS? Vapor pressure of solution, right? So, which is a greater value? Which is greater value? Yes, PA naught, right? So this is basically how much vapor pressure has lowered. So this is the lowering in vapor pressure. Is lowering in vapor pressure. How much pressure has been lowered by the addition of the non-volatile solute. And now if I say PA naught upon PS upon PA naught, this is the relative lowering in vapor pressure. And this relative lowering in vapor pressure is equal to mole fraction of the B. I can say it is equal to NB upon Na plus NB. For dilute solution, I can say the number of moles of the B is very, very less as compared to A. So Na plus Nb is same as equal to only Na. So Pa naught minus Ps upon Pa naught is equal to Nb upon Na. Am I clear, everyone? My dear, for this online class, be very, very certain point. I think Vedantu team might have given you certain instructions that you must be on time. It's not possible to repeat each and everything. We have to cover the syllabus and make you understand each and everything. And please, your connection should be absolutely perfect, no disconnectivity, as I have done at my end, right? At my end, there is a very, very least chances of disconnection, right? Students, if you're using something like what do you call laptop with a Wi-Fi connection, there may be some problem. Use a wired connection. Use wired connection with the laptop. Take the plug out from the router and put it in your laptop directly. That will give a clear signal. Clear? You must be computer savvy. I hope you are more computer savvy, right? I don't use all these things very frequently, but all of these things should be very clear. Okay, fine. Now come back. I'm repeating certain things. On this page, do you have any problem? I'm just repeating. The number of moles are Na and B. The pressure due to component B is 0 because it is a non-volatile, right? And the total pressure solution should be equal to sum of the two. But pressure due to B is equal to 0 because this is a non-volatile. So this is the definition of the Raoult's law. This is the definition of Raoult's law. That is the vapor pressure of a volatile component is equal to the product of mole fraction and pressure in the pure form. Is that clear? So I can now correlate here PS is equal to mole fraction of A into PA naught. That next is just mathematical operation, dividing, nothing else. Dalton law will not apply here directly. Yes, there is some special cases also there. We'll discuss it later. Fine. Now I can subtract 1 from both the side. The rest is again a mathematical operation, right? And now I have explained the chemistry. After this, I have explained the chemistry here, and all these are just mathematical things. Now, what is the PA naught minus PS? Lowering in vapor pressure. And if you divide by the PA naught, it tells about the relative lowering vapor pressure. And it is equal to mole fraction of B. The rest is all simple things. Now, do let me know if you find any problem now. Everything is okay? Fine. So NB means WB upon MB, and NA means WA upon MA. Students, if you are at your place and attending this class, attend it like as you are in the live class in your school or college. You must have a notebook with you. You must have a notebook with you. You must have a pen with you, and you are noting down each and everything. Right? You must be attending this class like as you attend in your schools or college. How is it equal to mole fraction? Okay, see, from the very clear, very starting is here, right? The total vapor pressure is equal to, right? Okay, fine. Now, based upon this formula, you will have some numericals. I'll be discussing some numericals later. Till now, any doubt? No doubt. Fine. Then wait a minute. Leave this. Raoult's law I have explained. This derivation I will not discussing for the non-volatile, for the volatile also. Yes, students, everything is clear now, I hope. Now, if we say now Raoult's law for solution containing volatile solute, now. Now, when we talk about the volatile solute, it means the solute is also evaporating. So I say component A and component B. A is volatile solvent. B is volatile solute. Its number of moles are Na, its number of moles are Nb. Pa naught and Pb naught are their vapor pressure in the pure form, and P and Pb are their vapor pressure in the solution. I hope all these terms are very clear. So according to the simple logic, the total pressure solution should be equal to the sum of these two, Pa and Pb. So now I am applying here the Raoult's law. Pa naught. What is Pa and Pb? Okay, I'll explain. This is the vapor pressure in pure form. This is clear. And this is the vapor pressure in solution. Okay. Now, this is equal to the mole fraction of A into PA naught. And PB is equal to mole fraction of B and PB naught. Now, I say the mole fraction of A is equal to mole fraction of 1 minus mole fraction of the B into PA naught plus mole fraction of the B into PB naught. I hope this mathematical operation is very clear now. Nothing much difficulty in it. Now it is PB XB into PA naught and mole fraction of the B into PB naught. So PS is equal to PA naught plus, take mole fraction of the B common, and now it is PB naught minus PA naught. Let me know if you have any doubt in any step. No doubt? No doubt. Very good. All of you are genius. It's very simple things. Yes, no doubt about this also that you're genius. Okay. Now, can I say this is equal to y is equal to mx plus c, a straight line equation? You can say y is equal to mx plus c, right? It is a straight line equation. So what I do is I make a graph between two things. Number one, vapor pressure, and number two, mole fraction. It's a graph between vapor pressure and mole fraction. And I say, suppose mole fraction of the A is equal to 1 and B is equal to 0. Can I say at this point? Yes or no? Okay. So if mole fraction of B is equal to 0, Pranav, we can solve it for n number of solid particles. But in your syllabus, it is only up to the binary solution, right? So I am considering here, Amey, that the solvent is only there, only solvent is there, solid is not there. Then mole fraction of A is equal to 1 and B is equal to 0. In that case, I'll put here XB is equal to 0 and the whole of this multiplication mathematical formula will become equal to 0, and this is the PA naught only now. Is that clear? This is the vapor pressure of the pure component here. Now, as I proceed toward this side here, the mole fraction of A will decrease and B will increase. And at the extreme, the XA will be equal to 0 and XB will be equal to 1. Is that point clear? Yes, Venkata, which is not clear? Let me know. As I move from left to right, the mole fraction of the A will decrease and the B will increase. At the end point, the A will become 0 and B will become equal to 1. And now when it becomes equal to 1, put here mole fraction of B is equal to 1. In that case, what will happen? PA naught and BA naught plus minus will be cancelled, and that will now left the B, only PB. And I say let PB naught is here. It may be above that also, because two liquids do not have the same vapor pressure, right? So it is straight line equation. So I'm drawing a graph straight line like this and straight line like this. I can say this is the mole fraction, vapor pressure B is equal to mole fraction into PB naught. I hope everything is clear. And here PA is equal to mole fraction of A into PA naught. So what you find here, At this point, let it be this point, there is some value of the mole fraction of the A, let it be 0.7 of the A and 0.3 of the B. So corresponding to this point, I can get the pressure of the component B. And at this point here, I can find out the mole fraction of the A component. Soumya Datta didn't get the graph. Okay. Okay, student, I am making this graph once again, but I'm starting from this equation. This equation is clear to all? Yes, Soumya. Up to this equation, this is clear to you? Fine. Now, the equation that is given to us is the mole PS is equal to PA naught plus mole fraction of the B into PV naught minus PA naught. I'm just drawing this graph once again. This is an equation Y is equal to mx plus c. It's a straight line equation. So if I draw a graph between two things, one is the vapor pressure and second is the mole fraction. Is this clear? So the graph is being drawn between the vapor pressure and the mole fraction on this side. And now I say mole fraction of the A is equal to 1, then B is equal to 0. At this stage, I say XB is equal to 0. It means the whole of this become equal to 0. So this is the PA naught. As I proceed from left to right, the mole fraction of the A will decrease and B will increase. And extreme, mole fraction of A will become equal to 0 and B is equal to 1. Is that clear? Fine. So when this point, only the component B is present and A is not present, right? So I'm putting the mole fraction of B is equal to 1 here. B is equal to 1 here. As I put B is equal to 1 here, PA naught and PA naught minus plus will be cancelled, and now I'm left with the only PB naught, and this PB naught is here. It can be about that also. It can be less than that also, but PA naught and PB naught cannot be same. I hope now it's very, very clear. Right. Now I'm just drawing a straight line as per. I'm joining, my dear. Give me some time. Now this is clear, right? So this is equal to PB is equal to mole fraction of B into PB naught. And this is the mole fraction of PA is equal to mole fraction of the A into PA naught. And now if I join these two things here, this is the total pressure here of the solution that is equal to A plus B. This is the graphical representation of the Raoult's law. What does the joining of the lines indicate? Joining the lines means which line? Blue line or red line? Blue or red? Red. Okay. So if you join this A and B points, mathematically only, let it be at this point, at this concentration, let it be equal to 0.6 of the A and 0.4 of the B. If I extend this here, this is the PB, it means I can get the value of the PB here, pressure of the B at this concentration. And if I join here further, this is the vapor pressure of the B, or the A only at this condition. And if I join upper limit, this is the vapor pressure of the solution. How do we get to know the blue first is XB PB naught? So how do you know to get it? It's a very simple thing. It's basically a a graph indicating the vapor pressure due to component P. When this becomes equal to 1, the pressure due to B will be equal to PV, not only. Right? Okay, one thing, you just keep on practicing this graph, understanding it. I'll discuss in the next class. First, you practice this graph. Right? Okay. Now, wait a minute. Because when you draw the graph again and again, understanding each and everything, you come to know each and everything. Right? Okay. Now, I have discussed here. Okay. Here is the problem. Can you solve it? Take your time. I'm giving you 1 minute to solve. Take your time. But xb is not always equal to 1 at no, I have not put x is equal to 1 at every point. At the two extremes only, I have put xa is equal to 1 or xb is equal to 1. It is not equal to 1 at every point. You can see the graph. Okay, now all of you, please, students, solve this question. I am now solving it. Let us see the method you have applied it or not. The vapor pressure of the pure liquid A, it means this is the value of the PA naught. Its mole fraction of the B is equal to 0.2, means this is the value that XB is given to you. And this total pressure solution is equal to PS. Calculate the vapor pressure of the pure liquid B. PB naught is to be determined. Right? So we know this formula, PA naught minus PS upon PA naught is equal to mole fraction of the B. Right? So PA naught is given to you, PS is given to you. So how do you get the value of the PB naught? Or you apply the formula PS is equal to PA naught plus mole fraction of the B into PB naught minus PA naught. Oh yes, you can apply this formula here. Right? Yeah, the same formula you can apply here. Find the PA naught value. Right? So 140 is the answer. Yes, Amay, you have given the correct answer here. Absolutely correct.